Chem 213, Exam 1 Material, Part 1. For this class, it would be best for you to go ahead and print out the lecture slides, the PowerPoint slides. You're going to be pausing the video quite often, filling in different areas, and then coming and checking your work. So the best way to get the most out of this is to work along with the PowerPoints and not just necessarily print them out or just watch the video. Be sure to be an active participant in your learning process. Benzene and Aromaticity. Aromatic compounds. Benzene is the parent of the family of aromatic compounds. Its 6 carbons lie in a plane in a hexagon. Each carbon has 1 hydrogen attached. Benzene is a resonance hybrid of 2 structures. You can see here between these 2 benzenes, I have the resonance arrow. Reminder, the resonance arrow is a single shaft arrow with 2 arrowheads on there, and that's when we're talking about the pi electrons moving around. We have delocalized electrons. Now these electrons are flying around so quick that at any one moment it feels as though, or the molecule feels as though, the electrons are almost in a donut shape around them. So it is acceptable for you to go ahead and draw the aromaticity of the benzene ring with a circle in the middle like I have represented here. If you're doing a nomenclature question or you're just drawing a structure, you can use either form. You can use the alternating double bonds or you can use the aromatic ring. If we're looking at a mechanism where we're going to disturb the aromaticity, it's best to use the alternating double bond so we can see how it's disrupted and how it is regenerated. In orbital terms, each carbon is sp2 hybridized. These orbitals form sigma bonds to hydrogen, and the 2 neighboring carbons are all in the ring plane. A p orbital at each carbon is perpendicular to this plane, and the 6 electrons, 1 from each carbon, form an electron cloud of pi bonds which lie above and below the plane. The way that I will represent that is I'm going to be putting on my drawing the pi orbitals above and below the plane around each double bond. And you can see as we go around the ring, once we have the double bonds represented, each corner, each carbon has its own pi orbital. So right now I have a carbon-carbon double bond represented back here with the pi orbital. What's going to happen is this pi orbital here is actually seeing this pi orbital over here being vacant and open. So this pi pair of electrons, these 2 electrons, are going to want to come over here. But the problem is we don't ever have 2 pi bonds or 2 double bonds next door to each other. It's always a conjugated system. And what's going to happen is as soon as this pair of electrons go over here, this pair of electrons is not going to be comfortable, so it's going to go over to here. And again, the same thing's going to happen. This pair is going to go here, and it's going to continue going around in a circle like that, and it actually goes pretty fast. So in terms of the pi bonds, they're going to be moving back and forth until they go so fast that it actually appears as though it is a single ring of electrons flying around there. So this model here represents the pi orbitals, and this one is when it starts flying around so fast being delocalized, what actually happens is a ring of electron density above and below the plane of the benzene ring. And that's why it's okay for us to show the aromaticity with a ring and not showing the explicit carbon-carbon double bonds. Because of the electrons being delocalized, the bond angles in benzene are 120 degrees and all carbon-carbon bond distances are equal. They happen to be 139 angstroms. This compound is more stable than either of the 2 contributing structures which have resonance, and we're looking at a stabilization energy of about 36 kilocalories per mole. The origin of the term aromatic comes from the description of fragrant substances such as benzaldehyde present in cherries, peaches, and almonds. This is the group benzaldehyde. It's one of them you're going to need to memorize. carbon double bonded oxygen with a hydrogen on one side. This is the aldehyde functional group. And when it's on a benzene, the whole compound has a common name, benzaldehyde. Today, aromatic refers to benzene and its structural relatives. Many compounds, synthetic and isolated from nature, are aromatic in part and include an estrone, morphine, and Valium. Sources of aromatic hydrocarbon come from coal and petroleum. They're two main sources for simple aromatic compounds. Coal has an array of benzene-like rings. You can see the structure on the bottom right-hand side. And some compounds that coal tar yields are benzene, toluene, naphthalene, and xylene. Now, petroleum yields many alkanes and only a few aromatic compounds. To start off with naming aromatic compounds, you'll be given some common names and structures to memorize. The first one being benzene. We've already seen that one. Toluene is when we have a CH3 group on there. Phenol is when we have an OH group on our ring. Aniline is when we have an NH2 on our ring. And xylene is actually a combination of two CH3 groups. It's not the same as toluene. And in fact, with xylene, we can have that CH3 group relative to the first one on there in three different positions. Those are the ortho, meta, and para. Looking down at the bottom of this slide, when we have both methyl groups on adjacent carbons in a 1-2 position, it's known as an ortho. Ortho, meta, and para are used specifically on benzene and when there's only two things on benzene. So the first time I'm introducing ortho, meta, and para to you is in the common names of xylene. So the structure I have in the upper right is not the actual structure, because did you notice my CH3 is not bonded to any carbons? This is a way that I can show you that it's going to be bonded somewhere else. If you're asked for orthoxylene, this is the format you would show me. Those are CH3 groups ortho to each other. If I ask for metaxylene, when you have the 1-3 position, that's when you have a meta position, so that would be metaxylene. And when you have the 1-4 position, then you would have a paraxylene. Continuing on with more common names to memorize, we have benzyl. With benzyl, we have a CH2 group here, and then more coming off this carbon as an R group. When benzene does not have priority in the naming system, it's known as a phenyl. And we're actually going to see the name phenyl used quite a bit because benzene is really low on the priority nomenclature. So we will see that quite a bit. Benzoic acid. Here we have a C double bond O, OH group on here. Sometimes instead of writing it explicitly as double bond OH, they'll write COOH. That is an acceptable way for you to do that. So this C here could be COOH. And your textbook does something interesting. They put CO2H. Instead of writing two O's next to each other, they do a subscript. These are all acceptable ways to represent benzoic acid when it's on a benzene ring. Benzaldehyde. This is the aldehyde functional group. And another way we could represent that would be CHO. The H has to come before the O. That's the standard notation to represent an aldehyde. So you don't have to explicitly show the double bond O, H. You can also write, coming off the benzene ring, a CHO. If you have the reverse of that, COH, you'd be having an alcohol. So it is standard notation to have the hydrogen first, then the oxygen when you're representing an aldehyde. Benzonitrile, we have the C triple bond N coming off of here. And again, this is another group where it's acceptable not to show the triple bond. CN is also acceptable. You don't have to put the triple bond between the carbon and the nitrogen. Benzene sulfonic acid, SO3H. Again, that's the correct order. Make sure you don't put the hydrogen somewhere else. This is the order it's always written. Benzene sulfonic acid, it's one of the compounds we're going to learn how to synthesize a little later. So in addition to the common names we just saw, we need to also be able to name monosubstituted benzene. A monosubstituted benzene that does not have one of those other common names is named by putting the substituent in front and following it with the name benzene. It's written as one word. Here we have benzene with the bromo on it. It is known as bromobenzene. Now sometimes you're going to see the benzene ring written as C6H5, and in this case because the Br is on there, I wanted you to see the molecular formula for that, and sometimes that's how they'll draw it. For this class, I want you to write the benzene ring, make sure you have the aromatic circle or the alternating double bonds, and then bromo could come off of any of those 6 corners. It doesn't matter which one you draw it off of because it's the same compound when it's monosubstituted. NO2 is known as a nitro group. This would be nitrobenzene. And this compound here has 3 carbons coming off of it. And because we could have the attachment on these 3 carbons on carbon number 2 instead, we have to indicate in the name where it's bonded to the 3 carbons. 1-propylbenzene, the 1 is not telling us where on the benzene ring it is, it's telling us on the 3 carbons of the propyl group where it is attached. In this case, it's attached to carbon number 1. 1-propylbenzene. The phenyl and the benzyl groups. Let's look at the phenyl group first. Phenyl is used when benzene ring does not have priority, and this is going to happen more often than you realize. Here's an example of when benzene does not have priority. Let's take a look at this example here. I want you to see that this set of carbons, the longest continuous chain regardless if benzene curves, has 7 carbons in it, and our benzene only has 6 carbons. A benzene is a hydrocarbon just like this chain over here is a hydrocarbon. They have equal priority, so the bigger one wins. If the straight chain has more carbons in the benzene ring, then this group here has to be named as a substituent. In this case, it's phenyl. Now, on this specific example, notice that my phenyl is coming off carbon number 2, and so that's why there's a 2 here. It's telling the reader that the phenyl is on number 2 of 7 that are single bonded. This 2 is required because couldn't you also have a 1-phenyl heptane? That's why we have to give the numbering system. Anytime we can move this somewhere else and it would have a different name, we have to have clarification in the name by giving it an address. You're also going to see sometimes the abbreviation PH for phenyl or the Greek letter in place of the benzene ring. We're going to see a couple more abbreviations for the benzene ring. They have a few of them. Now, a benzyl is different than a phenyl. A benzyl is when we have a benzene ring and a CH2 group, and then something else is attached to that. In fact, this carbon here is the benzyl position, and these are also known as benzyl hydrogens. Ortho, meta, and para. We did describe those before when we looked at the group xylene. These are relative positions on a benzene ring. This only happens when you have just 2 things and it has to be benzene. You don't use ortho, meta, and para on cyclohexanes, for example, or we would have brought them back up at that time. They're only used when 2 things are on a benzene ring. When you have something on the ring and it's next to it and it's a 1-2 position on an adjacent carbon, that's known as an ortho. In the name, you have to either write the word ortho or put an O to indicate its address. When you have something on the ring and if it's 2 away on the 1-3 position, then it would be meta. And when it's separated by 1, 2, 3, 4, 4th position away, then it would be at the para position. Here's some examples of naming. We have ortho dichlorobenzene. It's a 1,2 disubstituted benzene. Metaxylene. This is a 1,3 disubstituted benzene. And parachlorobenzaldehyde, a 1,4 disubstituted benzene. When we first introduce ortho, meta, and para, we tend to use the same groups coming off in the ortho, meta, and para position because what that does is it allows the name to be much shorter. These 2 things that are ortho, meta, and para to each other do not have to be the same, and that's illustrated in this last example here. This on the right-hand side is an aldehyde group, and over here is a chloro. It's only relative positions to each other. not the identity. We can also use ortho, meta, and para to describe what can happen during a reaction. So we could say this reaction occurs at the para position, and then we'll know that the bromine is going to go para to our original CH3. Naming benzenes with more than 2 substituents. If it's not a common name compound, what you need to do is look for the lowest possible values as you go around the benzene ring, similar to how we did when we had cyclohexane. We also list the substituents alphabetically with hyphenated numbers. What I'd like you to do on this slide is to go ahead and name these on your own. I want you to pause the video, and from the name, I want you to go ahead and draw the structure and come on back and see how you've done. 4-chloro-1,2-dimethylbenzene. We would start off drawing a benzene ring, and in position 1 and 2, you would have 2 methyl groups. 1, 2. Now I can go clockwise or counterclockwise because these are next door to each other. But the way I have mine drawn, the numbering system actually would go in this direction. Here's carbon 1, 2, 3, and 4. Another thing I could have done is I could have made this 1, 2, 3, and then I would draw my chlorine here as 4. When you're drawing the structure, you get to establish, as soon as you put down the first substituent, you're establishing carbon number 1, and then after that you get the choice of going clockwise or counterclockwise. But once you choose a direction, you must maintain the direction for the rest of the molecule. If you were given the structure and asked for its name, and you needed to write down its name, remember that the di in methyl is not used in alphabetizing. It's only the M that is used in alphabetizing. Multipliers are never used in alphabetizing for determining what order the substituents go. 1-bromo, 3-ethyl, 2-nitrobenzene. In this case, we have a 1, 2, 3 situation going either clockwise or counterclockwise. So if we were given the structure and asked to name it, we see we have an ethyl and we have a bromo. If I were to look at prioritizing, because they're equal priority, if I were looking at which one would have priority over the other, it'd be alphabetical at this point. So bromo gets to be on carbon number 1, and the direction must go in here counterclockwise. Also, I want to mention sometimes you're going to see ethyl written in this molecular formula way, and I need you to be familiar with that. C2H5 is an abbreviation for ethyl. Common names such as toluene can serve as the root name. So if you have a common name in your compound, you need to use the common name, and then the carbon that it's attached to automatically becomes carbon number 1 because it has priority. Unlike these compounds above it that didn't have the common names, where we only had priority with physical location, is because all the different substituents had equal priority. When you have a common name, such as toluene, that has priority. 2,4,6-trinitrotoluene. 2,4,6-trinitrotoluene. I underline the TNT because this is TNT. Here is the toluene piece. This gets to be carbon number 1. And this is a very symmetrical molecule. So if I went clockwise or counterclockwise, I'd still get the same numbers for my 3 nitros. 2,4,6-trinitrotoluene. Here I have 5-bromo, 2-chlorophenol. So the first thing I would have as priority would be phenol. The carbon the OH is on would be carbon number 1. Since this is carbon number 1, I would go in the direction that would have the next substituent have the lowest number. So that would be counterclockwise the way I have it drawn, where chloro is on number 2 and bromo, because remember, once you choose direction, you maintain the direction for the rest of the molecule. The bromo is on 5. Here we have a benzoic acid, and in this case, I have O in front of it, and that means ortho. So you can either write out the word ortho or O, and there is a dash on location between the O and the BR because it's a position, it's an address. This is carbon number 1, and coming down this way, in this case clockwise, bromo is on carbon number 2. So I can name this compound one of two names, orthobromobenzoic acid, or I could have, instead of the ortho, put a 2 there and have it 2-bromobenzoic acid. Both are acceptable. All right, I have 6 structures on here for you. I would like you to go ahead and name these. Pause the video and come on back and see how you did. Okay, on letter A, these all have equal priority, so it's the physical locations to give the lowest possible number. This right here would be 1, 2, and coming around here in this direction would be 4. We list them alphabetically. Bromo comes before chloro. And remember, again, in the name, when you list them, the multiplier doesn't count alphabetizing. So this would be a 2,4-dibromo 1-chlorobenzene. Anytime we have numbers and numbers, they're separated by commas. Number and letters are separated by dashes. Okay, on letter B, we have all of these having equal priority again. So we have a 1, 2, 3 situation if I go clockwise. If I start down here and go the opposite direction, I also have a 1, 2, 3 situation. So how I break the tie is alphabetical. This NO2 is a nitro group, and C2H5 is an ethyl group. E comes before N, so this gets to be carbon 1. This is carbon 2. This is carbon 3. And we do not use the multiplier. This will be dinitro. We don't use the D in di to alphabetize it. It's only the N in nitro. Letter B is 1-ethyl 2,3-dinitrobenzene. For letter C, we have a 1, 3, 5 situation no matter where I start. Take a look at that. So they're equal priority. Where do you start? Well, alphabetically, Br comes first. So we're going to start here. This is going to be carbon number 1. Now, do I go clockwise or counterclockwise? Well, in the clockwise or counterclockwise direction, I get the same number. Doesn't matter. So now I have a tie. How do I break a tie again? Alphabetical. F comes next, so I'll be going in this direction. So this would be 1, 2, 3, 4, 5. Remember, once you choose a direction, you maintain the direction for the entire molecule. List the substituents alphabetically. 1-bromo, 3-fluoro, 5-iodo benzene. In letter D, I have a common name. This is aniline. And because there's only 2 things on the ring and it's a benzene ring, I can use the ortho-meta-para system. So which one is this? This one's meta. Metachloroaniline. On letter E, again, I have a common name. This is benzaldehyde. Only 2 things on the ring. So I can use the ortho-meta-para naming system. This is para, so I would use P in its name. Parachlorobenzaldehyde. On F, I have a substituent coming off here that happens to also be cyclo. When it's not the parent, it would be named as an alkyl name, cyclopentyl. Remember those alkyl names? For example, look back at letter B. This is ethyl. It's not ethane. We took the A and E ending and put YL instead. You do the same thing if it has a ring. This is a cyclopentyl group. Cyclopentyl benzene. There's no number used because I could have put my cyclopentyl on any of these 6 corners and it would have been the same compound. The structure and stability of benzene. Benzene is very stable. It undergoes a slow substitution reaction where the ring itself does not react. There is no addition product formed. Here's an example of a halogenation reaction. We have benzene, and X2 could be either chloro or bromo, and then it needs a catalyst, in this case an iron catalyst with one of the halogens. Well, with this reaction, what is required is if this X2, if you're trying to put chlorine on the ring, then your catalyst must also have chlorine. You can't mix them up, otherwise you'll get a mixture of products. So if you intend to do a chlorination, this must be Cl and this must be Cl, and the subscripts are still going to be the same subscripts. So if I had a bromination reaction, This would be a Br, and this would also be a Br. So how do they know that the ring itself doesn't react? They have different evidences of stability. In fact, there's 3 of them here. The heat of hydration is 150 kilojoules less than expected, so it's 150 kilojoules more stable than expected. Another evidence is that all the carbon-carbon bonds, both single and double, are the same length, and also the molecule itself displays resonance. Looking at the molecular description of benzene, the 6 pi orbitals combine to give 3 bonding orbitals with 6 pi electrons, 2 non-bonding and 2 anti-bonding orbitals. When you have orbitals with the same energy, they degenerate. Let's take a look at our 6 atomic orbitals. Anything that is a higher energy is going to be anti-bonding. Anything that's the same energy, we don't have anything there, would be non-bonding, and anything below it would be bonding. The next thing we have to keep in mind is that all the orbitals in the ring, do you notice how these are all shaded pink and these are all kind of white? All of the orbitals have to be the same. Like in this case, all the pinks have to be on top together and the whites below it. So this is the orbital that we are going to use to represent the picture of benzene. Aromaticity and the 4n+2 rule. So we've already talked about benzene being aromatic. There's other compounds that are also aromatic, but we have a few things we have to look at before we can call them aromatic. First of all, we have Huckel's rule, and this is based on calculations. It's going to be stable if it follows the 4n+2 pi rule. Now, that's not the only thing we look at. The molecule itself must be planar, cyclic, and alternating double and single bonds. So one of the first ways we can take a look at a molecule is if it passes the 4n+2 rule, then we'll look for planar, we'll look for circular, we'll also look for alternating double bonds. But if it doesn't pass the 4n+2 rule, it is not going to be aromatic. So knowing that benzene is aromatic, let's use that as our first example. It has 6 pi electrons. Every double bond has 2 pi electrons, and I have 1, 2, 3 of them. So that's 2, 4, 6 pi electrons. How the 4n+2 rule works is you have 4n+2 and you set that equal to the number of pi electrons. We then solve for n. If n is a whole number, could be 0, 1, 2, 3, 4. If n is a whole number, then it's aromatic. If it is not, it cannot be aromatic. So when we solve for n for benzene, n equals 1, that is a whole number, it is aromatic. Now, not all compounds that meet the 4n+2 rule are aromatic. They could be anti-aromatic. Planar cyclic molecules with 4n pi electrons are much less stable than expected. They're anti-aromatic. They will distort out of the plane and behave like ordinary alkenes. That means you can do an addition across the double bond. 4 and 8 electron compounds are not delocalized. So here we have an example here of cyclobutadiene. It is so unstable that it dimerizes by a self-Diels-Alder reaction at low temperature. Another example here would be cyclooctatetraene. It has 4 double bonds and will distort out of the plane. So we don't have a planar molecule, so now it can't be aromatic. So what you can do with this is you can actually do an addition reaction and you can add across the double bonds. Again, aromatic compounds cannot have an addition reaction across the double bonds. The 4n+2 rule also applies to ions as well as neutral species. Both cyclopentadienol, anion, and cycloheptatrienol, cation, are aromatic. Because of this pair of electrons here, the electrons are able to come around and form a ring structure and make this especially stable. And because we have a positive charge here, a similar thing happens. The electrons are attracted to it, and so we can have the electrons move around in it, and it is also aromatic. The key feature of both is they contain 6 pi electrons in a ring with continuous p orbitals. Aromatic heterocyclose, pyridine and pyrrole. Heterocyclic compounds contains elements other than carbon in a ring, such as nitrogen, sulfur, oxygen, and phosphorus. So we have 2 examples here with nitrogen in the ring, and both of these are going to be aromatic. In pyridine, the nitrogen lone pair electrons are not part of the aromatic system. It's perpendicular to it. So the electrons can still fly around and form the aromatic feature. So looking at the structure here, we have alternating double bonds. So this is aromatic. Now contrasting that with pyrrole, the nitrogen atom is sp2 hybridized, and because it's sp2 hybridized, the pair of electrons that it has is actually part of the ring itself in this 5-membered ring, and it is also aromatic. Both of them have 6 pi electrons, they're planar, and they have alternating bonds. Polycyclic aromatic compounds include naphthalene. This is when we have 2 benzene rings fused together. Anthracene would be 3, and then we have a couple more examples here. These follow Huckel's rule, and we'll also see that they are cyclic and planar. On naphthalene and also anthracene, because we know that it's aromatic, one of the ways you can draw it, you do not have to draw the alternating double bonds. Because we know it's aromatic, you can use the aromatic circles instead. So my circles, they're a little crude, a little messy, but you can see that the top here, this would be an acceptable drawing for naphthalene and also anthracene. And naphthalene and anthracene are 2 common names and 2 structures of polycyclic aromatic compounds that you will be responsible to know. So if you notice in your PowerPoint lecture, I have naphthalene and anthracene circled, and that's because those are the 2 common names that you need to have memorized, the common names and the structures. Here's 3 resonance structures of naphthalene. One of the things we've learned about resonance structures is the more resonance structures it has, the more stable it is. So we have 3 resonance structures. This is an extremely stable compound. And you can see here that we have a drawing showing the pi orbitals, and we also have a drawing showing the aromatic circles. Spectroscopy of aromatic compounds. In IR, the aromatic ring, carbon-hydrogen stretching, we have a peak at about 3030, and there's additional peaks at 1450 and 1600. If you have a monosubstituted ring, you'll also see some peaks over here at about 700. Because benzene is a conjugated system, we do get a UV peak near 405 nanometers and a less intense peak at about 255 to 275 range. Proton NMR, the hydrogens on a benzene ring are somewhere between 6.5 and 8. They're very far downfield. So this is the proton NMR for this compound here. We have 3 hydrogens on our alkyl group, and so those are going to be at about 2. Normally they're about 1 or less, but because it's on a benzene ring, it is pulled further downfield. Now, when you have your benzene, your aromatics, typically they don't split like you would expect by the number of hydrogens. But one thing we can definitely see here is, do you see these 2 peaks here that are separated? This right here is the classic pattern for a para-substituted aromatic. It's a good thing to have in your arsenal when you're trying to figure out structures. The classic pattern for a para on a benzene. The reason why benzene is so far downfield is because it makes its own ring current. The circulation of pi electrons induced in aromatic rings by an external magnetic field, this effect accounts for the downfield shift of aromatic rings from around 6.5 to 8, compared to the vinyl, which is around 4.5 to 6.5. The presence of the ring is characteristic of all Huckel aromatic molecules and is a good test for aromaticity. This is a picture of the benzene ring and its own magnetic current that it actually displays because of that ring. Carbon NMR, the aromatic ring has absorptions of about 110 to 140. This shift is again distinct from other compounds. It's away from the alkene range. It's further downfield. And here's some examples of different values for different pieces of the different aromatic compounds. Aromatics on carbon NMR, about 110 to 140.